Hi everybody. Today we are going to talk about imaginary numbers and how they are involved with quadratic equations. Okay? So in the last video we talked about the square rooting method. So let's try to solve this equation with our square rooting method. Okay? We know we can use it because we're missing the bx part of the equation. So we're going to get x squared by itself, square root both sides, and that's where we have an issue. We can't take the square roots of a negative number. So what mathematicians decided was, since this comes up, we're going to actually define the square root of -1 as the imaginary unit I. So what that allows us to do is it allows us to continue to solve equations like this that we wouldn't be able to solve otherwise. So the solution to this equation actually ends up being x equals plus or minus I. Okay, so it's useful when we're working with square roots of negative numbers. It allows us to continue solving things that would otherwise be unsolvable. So let's look at some negative square roots here. Okay, so I've got two different square roots. We have the square root of -196 and the square root of -80. Now, before we try to break down the square roots any further, I want to show you how we take care of that negative part. Just like we did in the last video, we're going to start by splitting this into two pieces. I'm going to split this into the square root of -1 times the square root of 196. And the reason I do that is because we know that the square root of -1 is just I. So now I have I times the square root of 196, and I can continue breaking it down from there. Okay? Well, the square root of 196 is just 14. So now I have I times 14. Typically, and the way that I want you to write it is 14i. We always want the number before I. So let's do -80 here. Just like the last one, we're going to start by splitting that into -1 and 80. Okay, we know the square root of -1 becomes I, and that allows us to focus just on breaking down the square root of 80. Okay, so the biggest perfect square that's a factor of 80 is 16. So we're going to split that into the square root of 16 times the square root of 5. Okay, we know the square root of 16 is 4. So we have I times 4 times the square root of 5. And again, the order here is important. We want it to go number first, then I, then our radical. So that's how we would break down the square root of a negative number. That negative is really going to come out and just become an imaginary unit outside of your radical, and then you can continue breaking the square root down from there. So let's look at some equations that have that involved. Okay, we're still going to use our square rooting method because we're missing the bx part. So we're going to isolate x squared. I'm going to subtract 9 first, and then divide by 2. And then we're going to square root. Okay, and before we said that's an issue because we can't square root negative numbers. But now we know that we can just use imaginary numbers to help us out. Okay? So really, this is splitting into the square root of -1 times the square root of 4. I know the square root of -1 is I. I know the square root of 4 is 2. So our solution is plus or minus 2i. Okay, let's look at another one. All right, I'm going to isolate x squared again. I'm going to subtract 13. And then we're going to square root both sides. So we get x is equal to plus or minus the square root of -12. So let's start by taking out the negative first. Okay, so we know the square root of -1 is going to turn into I. And then we can break down the square root of 12. So the biggest perfect square that's a factor of 12 is 4. So I'm going to do the square root of 4 times the square root of 3. And our solution is plus or minus 2i square root 3. So we're still using the square rooting method there. We're just looking at solutions that we typically would have said had no solution. Okay, if I can't square root something, then before we would say that's not possible, there's no solution to this equation. Okay, and it is true that if I were to graph, let's say I would need to rework some things, I would have to get everything to one side, but the corresponding function for this would be f of x equals 2x squared plus 8. If I were to graph that, you're going to see it kind of just like floating somewhere above or below the x-axis. It's not going to actually be touching. Right? So that's what we're looking at here. There's still imaginary solutions, but you're not going to actually see a 0 or an x-intercept on the graph of that corresponding function. So here's the last thing I want to talk about. I want to talk about powers of I. What happens if we have I squared, I cubed, and so on? Well, we can always break it down into smaller units of I. We know by definition I to the first power is just the square root of -1, and we just use I to represent that. Well, what if I had I squared? Okay. What if I had I squared, which would really just be negative, or the square root of -1 in parentheses squared, because I know that this is really just I. Well, if I square the square root of -1, I get -1. So strangely enough, when we square an imaginary number, I, we get a real number, -1. So let's continue. If I cube I, okay, let's think about this as I times I squared. Okay, well, I is just I, but we just said that I squared is equal to -1. So I times -1 would just be -I. So anytime we have I cubed, we can reduce that to -I. I to the fourth, we can think about that as I squared times I squared. Well, we know I squared is -1. If I have -1 times -1, that's going to be a +1. I to the fifth power we can say is I times I to the fourth. We know I to the fourth is really 1, so I to the fifth power reduces down to I, which is the same as what we had here. Let's see, I to the sixth power, let's do I squared times I to the fourth. We know I squared is -1. We know that I to the fourth is +1, so this is going to be -1, which we already saw here. For I to the seventh, let's do I to the fourth times I to the third. I to the fourth is 1. I to the third is -I. So that's going to give us -I. So again, we're starting to see that this pattern is repeating itself. All right, so if we had to take a guess, okay, the pattern is going I, -1, -I, 1. I, -1, -I. I'm going to guess that the next one is going to be 1. So let's check ourselves. We could rewrite I to the 8th power as I to the 4th times I to the 4th power. We know that I to the 4th is really just 1. So if we have 1 times 1, we're going to get 1. So the important thing to know here is that this pattern repeats itself over and over and over, no matter how high of a power of I you have. The reason that's important is because we can really only care about these first 4. Okay, we're going to think of these first 4 as our building blocks. We can construct any other power of I using these first 4 powers of I. And this is something we'll talk about more down the road, but this is the beginning of these different powers of I. Okay, you always want to reduce it as much as you possibly can, because it's going to make working with your imaginary numbers a lot easier. All right, guys, let me know if you have any questions, and have a wonderful day.